Hello children, welcome back to CK classes. And today, we will discuss the decimal expansions of rational numbers and irrational number. A concept comes under ninth standard's ninth what number system. So, let us begin with the some different types of decimal expansions. Just I'll write some of them. Correct. 0.125, 0.3333, 0.12, 1, 2, 3, 4, 1, 2, 3, 4, 5, and keep on writing like this. Look at three or different type of decimal expansions. So these are the expansions you got from by using rational or irrational numbering cases. So now 0.125, it has been, you can say you can't find any continued version of a continued part of 0.125. You can conclude yourself 0.125 has been stopped. Here the same number it went on repeating, just like 3, 3, 3. So you can represent by this one by using certain symbol like the 0.3 bar. You can say the repeating block or repeating part can be represented by using a sign like you can say 3 bar. The 3 bar represents a 3 is going to repeat again and again and again. Look at the third one, it's a bit different compared to these two. Here it looks like the numbers are recurring, but actually they are not recurring. Even one can say then not repeating at all. 1 2 1 2 1 2 3 1 2 3 4 1 4 1 2 3 4 5 just went on, but not without repeating the what numbers are continuing. So now let me name all three decimal expansions. So these kind of expansions we can call them as a terminating decimal expansion. You can say terminating decimal expansion. Terminating decimal expansion. You can say terminating decimal expansion. It's a one. It's very one. A repeating decimal expansion. I can call RDE. You can say a repeating or recurring decimal expansion. This is very important. Non-terminating, non-repeating decimal expansion. It's very easy to memorize all these one by using simple codes NT, NRDE, RDE and TDE. So which one? Here TDE meant terminating decimal expansion. This one is repeating or recurring decimal expansion. This is non-terminating and non-repeating decimal expansions. So there are three kind of decimal expansions you can you can get by using real numbers. So let's get into the decimal expansions of rational numbers and irrational numbers. In the beginning, just see, I'll take one example. So draw this. Okay, 1/3. So I'll find decimal expansion of 1/3. It's very simple. I'll try to divide 1/3. Although 1 will never divide 3. You can say 3, you can say 0. If you put it, you get 10 here. 3 3s are 9. So 1 is going to remain. Again, after putting this, you can take 1 0 there. 3 3s are 9. Again 1 0. 3s are 9. Again 1. So you can say just keep on continuing. Therefore, you can say 1/3 as something called 0.333 and so on. This you can represent by sign. I told us I mentioned already. So 0.3 bar. This is a recurring decimal expansion. So let's go to get into another one. Something I'll take 5/8. Look at this one. So I will try to divide 5/8. You can say I know 5 will not go by 5. I will go for 0.86 are 48. Again 2 is going to remain. You can take 0. 8 2s are 16. So 4 is going to remain. I can take 0. 8 5s are 40. So what's the conclude that is you got remainder as 0. You can't continue further. So at last you can conclude yourself 5/8 will be equal to 0.625 So that is what I say terminating decimal expansion. So I'm concluding by using these two examples. So very important point. So the decimal expansion of rational number always either terminating or recurring. Then what about irrational numbers? The irrational number decimal expansions are totally different compared to them. So irrational numbers, what decimal expansion is always, I say that's non-terminating, non-repeating. So they won't repeat it and they won't terminate also. I'll write some of the examples for you. I can say 0 0.1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. Look at this one. These numbers will say even none of the numbers but repeating back are the what even they won't terminating. In that case, you can say these are the what examples of what decimal expansion of what irrational numbers. So I can write some more like this is 1 0 1 0 0 1 triple 0 1 4 zeros and keep on writing. So at last I can concluding in again regarding to irrational numbers. The decimal expansion of irrational number is always a non-terminating and non-repeating. So these 2 points keep in your mind. So this will help you to what distinguish between irrational numbers and irrational numbers. So you can take some examples of root 2, root 3, root 5. In general, root p is what irrational, where p is the prime numbers, or non-perfect squares if you take it. So in all the cases, irrational numbers, they will give you a non-terminating and non-repeating decimal expansions. So now let's get into one simple, interesting concept of what representation of irrational numbers on the what number line. So and also if you want to represent some irrational numbers on the number line, I'll take help of Pythagoras theorem, what we have, which we have discussed in the discussed in the previous video. So how that Pythagorean theorem will help us to what represent some irrational numbers on the number line. So let's see today. So now first question I'll take is very important one. Represent root 2 on number line. Okay, represent root 2 on number line. So to represent root 2 on number line, just I'll take help of a right angle triangle. So I'll call this is a right angle triangle A, B and C. So for this one, for the what you can say, I can go for the technique called a trial and error technique. Trial and error technique. So I'll fix somewhat base size here. Like I said, based on that, I'll take 1 unit here, even 1 unit here. So what is going to happen? And since I mentioned it's a right angle triangle, since angle B is equal to 90 degree, so this implies, so you can use Pythagoras theorem. Since angle B equals 90 degree, you could write it as square on hypotenuse is equal to sum of the squares of those two sides, AB square plus BC square. So now AB, just you got 1 unit, right? That is 1 square, plus BC is 1 square, again AC square, is 1 square plus 1 square, that would be equal to what? So 1 square, 1 plus 1, that is 2. You need AC square, you need AC. Now just get rid of, how do you get rid of square? That is by taking square root on both sides. If you take square on both sides, you can cut this one, square and square will cancel. Therefore, AC is equal to root 2. You got it. This is very important one here. So I got root 2 here. So that's how to represent this situation. The number line is very different. Okay. So I'll help you now. Suppose I'll block a small block here. So this construction you need some apparatus like a scale, a protractor and a compass. So you need these 3 instruments to represent root 2 on number line. So first basically you have to draw an horizontal line, and if say a 0 or origin there first, 0, and take, I'll write some scale, take 2 centimeter is equal to 1 unit. This is very important one. So to looks what this diagram neat and clean. So best you take 2 cm as 1 unit. In that case 2 cm you take it as and mark for 1 unit and mark for another 2 cm, mark for 2 units. This was what fundamental. Now I want to take 1 unit here, then I just want you to mark it. This is very important one. So now at the 1, you just use a protractor and mark an angle of 90 degree. So I am not using any protractor, just using for general purpose I am marking. So you just draw a light line. Yeah, this is what perpendicular one I have drawn, this one. Okay, here the important thing is, again you have to mark for here 1 unit because you have taken here 1 unit. Again you have taken here 1 unit. I told 1 unit will be 2 cm. You can see mark for 2 cm here. So approximately I am marking here. Again I took 1 unit here. So I think you got almost similar to this one. Now you just join. You can call this point as A. Just you want to mark it. So just join. So this point to this wall. Yes, you got a right triangle there. You can observe right angle triangle here since you have taken 90 degree there. Oh, it's not right. Good. You can observe a 90 degree there. Okay. So now, if it is 1 unit, this what diagram will help us, what actually length from here to there. So better let's mark it then, and it will be nice to what protect this point you call it as A, and this point you call it as B, and this point you call it as C. Now what is AC actually? What the length of AC? The length of AC they have given us, what can I say? Root 2. So I got this root 2. So now I just say I represent root 2 here, but I want to represent root 2 on this number line. So for that cases, so I don't have this one. Which one? A compass, but you can use a compass. Now take this one, the measure from this to this, this length, and this, here. So this length represent exactly root 2. Now I am represent by using number line. Just have a look here. See that? Just just see at this point. So this point represent a root 2. So now you can say this is root 2. I know that as the value of root 2 will be approximately equal to 1.41 something. So you got actually 1.41 something. So this is how you can represent what irrational numbers on number line with the help of Pythagorean theorem. So now just this is what basically I told before I could proceed with what root 2 is irrational. I told that is trial and error technique. What does it mean? How does it help us? So in mathematics, in most of the cases or most of the problems, we will approach this method called trying and making errors and get some results. Suppose if you ask another one, like if I ask me to what represent root 5 number line. So that if I ask this root 5, look at the variation, root 5 I could take. So in that case, so how there's two things it's going to change. Let's have a look. I'm changing up this. Just because I know the basic this one things and all we need. Okay. This will mark this is 1 and this is 2. So here, what value should I take for the basis to get here a root 5? I need root 5 here. Here I should fix some what results. Okay, say I can check this one now. I don't want them. So here the same conditions is angle equals B equals 90 degree, AC square is equal to AB square plus BC square. So now it's time to fix the sides. So let's have a look what I'm going to do. Here I'll take 2 units. Here I'll take 1 unit. You can say 2 units and 1 unit I'll take. So just say now this was my prediction So you can take 1 and 1, you won't get it. Just I modified with what 1 with 2. Let's see what is going to happen. AB square, that could be 2 square, and BC square, that could be 1 square. 2 square is 4 and 1 square is 1, it could be 5. That is AC square. Just to get rid of what a square, you should go for square root. Take square root on both sides. Square and square will cancel. At last you get AC is equal to what? 5. That is root 5. So now you can say to get root 5 you need 2 units and 1 unit. In that cases, let's modify here. You take 1 more unit, that would be 3. So first they will just fix for 0 to what? 2 units. Take 2 units here, and that cases 2 units at 2 units at 2. So using protractor, mark an angle 90 degree. So after marking an angle 90 degree, you just draw a line. So I'm not using any scale. Hope it could be a perpendicular to this one. Now you have 2 units here. So now you have to take this one as 1 unit. As I mentioned, 2 centimeters equal to 1 unit. Just mark for 1 unit. Just see now I'll take this as 1 unit. Okay. So I'll call this point as A, and this point as B, and this point as C. I already marked it. It is helping me. So now I have taken here 2 units, here 1 unit. So now let me join AC. So what is the length of AC right now? Here I got it how much now? It could be a root 5. So now I'll do this again. I'll take help of what? The what compass. It's my compass. You can change the compass by yourself. You can use the compass. Length of CA. Just have a look. The length of CA is a root 5 length. You can say it's a root 5 length. So I'll represent a number line just like this. So this point represent a root 5. So that is how you can represent irrational numbers on number line. Thank you.